Hello, everyone. So my name is Dani Leonard. I'm at Newcastle University. I'm going to start us off by speaking about astrophysical systematics for weak lensing and clustering with a focus on LSST. So I'll talk about four different types of systematics we might care about, but I'll get into that. I know we have a variety of people with different expertise. So I was going to give a quick introduction to weak lensing just to remind us all what we're talking about. So these figures, this figure and the one on the next slide, are credit to Jesse Muir. So to remind us all, so when we're talking about weak lensing, we're talking about the scenario where we have a source of light far away from us as the observer. And in this talk, those are going to be galaxies. So we have a galaxy, which we call a source galaxy. So those are these ones out here. And they have some light coming from them. And they have some sort of like intrinsic, image that we would see of them were there nothing in the middle. But in fact, of course, there is something between us and them, which is, the cosmic matter distribution, structure, dark matter, other galaxies as well. And so the light coming from the background galaxies is lensed as it progresses through this field of matter. So its path is changed, and as a result of that, we see distorted images of the background galaxies. Now, this is wildly exaggerated for weak lensing. This might be more what we would see in the case of strong lensing. And for weak lensing, we're talking about the case where these differences are very small, so we can only detect them statistically by looking at correlations. But we can imagine that if we do this, we can learn something about the physics of how the light path is changed, and we can learn something about the dark matter structure that's intervening, as well as maybe the other galaxies. So that's the refresher on weak lensing. So I'm going to talk about weak lensing and clustering, and I'm going to talk from the perspective of 2-point statistics. So I think maybe Lila will speak a little bit about higher order. Sorry, Lila, if that's not your plan. But I'll talk about 2-point statistics. And so this is basically trying to extract information about weak lensing and galaxy clustering using statistics about pairs of galaxies. So again, I know most people might be familiar with this, but just as a refresher, we have the effect of weak lensing, and one way we might measure these tiny correlations, these tiny distortions in the galaxy images, is by looking at, say I have a galaxy at a certain location on the sky, and I have its position, and I can measure things about it, like its shape, its brightness. Usually we measure shape to talk about the distortions due to weak lensing. So I asked the question, okay, if I have a galaxy in this position on the sky with this sort of shape, what is the probability, the excess probability above what we'd have for a random field to find another galaxy at a certain angular separation with a certain shape? So that we have a measure of the correlation in the shapes, and we expect that this correlation in the shapes is primarily due to the lensing effect. There are other things that can cause it, as I'll get into. So that's the case where we're looking at correlations between shape and shape. So that's kind of lensing. So we call that cosmic shear. So that's one kind of 2-point function. The case of looking at 2-point functions for clustering is arguably simpler. So in that case, I'm talking about photometric clustering. So I'll talk about angular separations. So no spectra. But if we're looking at photometric clustering, we would say, okay, I have a galaxy that I don't care about its shape. I just know that I have a galaxy at a certain position on the sky. So I have that galaxy, and the question is, what is the excess probability above random to have another galaxy at a certain angular separation, just to have it there, not anything about its shape? And so that's going to tell us something about the clustering, right? So that's our clustering 2-point correlation function. And then, of course, you can do the cross between the two. So I'd say I have a galaxy with a certain position. How is that correlated with having galaxies of certain shapes at a certain separation above random? So we call the lensing or shape 2-point function. We talk about that as cosmic shear. we call the clustering one clustering often, and then we call the cross one galaxy-galaxy lensing. As you can imagine, we have a galaxy in the foreground tracing the dark matter, and that's going to be correlated with having lensing by that dark matter in the background. So we call this our 3x2 point type analysis because we have 2-point functions and there's 3 of them. Okay, and then the last sort of setup thing is we're not just doing this all in one redshift bin. We don't have spectroscopic redshifts in this case, but we do have some redshift information, right? We have photometric redshifts. So we try to bin our galaxies into redshift bins, and we kind of talk about having 2 samples. So we have a source sample, and these are the galaxies for which we are thinking about measuring their shapes for lensing. So these are going to be ideally at a slightly higher redshift or extending to higher redshift, and we're going to have many, many, many of them. And then we're going to have a lens sample, which are going to be the galaxies for which we're thinking about the clustering and going to act as like the lens tracer in the galaxy-galaxy lensing. So not the galaxy of which we're measuring the shape, but the ones which we're only caring about the position. And then we try to bin those into different samples according to redshift using photometric information. And then we do these cross correlations that I mentioned across and within different redshift bins. So even though we don't have spectra, we get some redshift dependent information. Okay, so that's the kind of data. This is sort of what that data vector looks like. So this is from Dark Energy Survey, not LSST, because we don't have data from LSST yet. But just as an example, so this is the galaxy-galaxy lensing, so that's shape cross position case. And so here we have in Fourier space, we have each of these little squares is the Fourier space 2-point function of the galaxy-galaxy lensing, so position cross shape. Inside each square, so we see that we're in terms of L, this is a 2-dimensional, an angular Fourier space variable. So the larger L are actually smaller scales. So as you go right in each square, you're going to smaller scales. So each little square is a 2-point function, and then the different squares are the different crosses between the redshift bins. So they're, we have 1, 1 that's within the first redshift bin, 2, 4 is second redshift bin of the lenses cross 4th of the sources, that kind of thing. Okay, and so the game here, as some of you will be intimately aware, and others probably have heard at some point, is to try to use this kind of measurement together with the cosmic shear equivalent and the clustering equivalent to constrain our cosmological model, do model comparison, all that good stuff that we all care about. And so, of course, we're here to talk about things like systematics. So cosmological model, maybe it's 6 parameters, maybe it's 7 or 8 if we're getting really, exciting. But of course, the best fit model here, which is shown in red, also includes many systematics parameters. And so that might be 20 to 30 in this specific case. And we also have, you might be able to see some scales that are grayed out in this figure. So as I said, the larger L are smaller scales. So those are actually small scales, cosmologically speaking. And so we've actually, in this case, this analysis here has cut those smaller scales entirely because of modeling uncertainties. So this is to kind of give a flavor of what we're talking about here. Okay. And of course, we all know, statistical uncertainty is getting smaller. We care more about these systematic things. So for lensing, upcoming stuff we care about, obviously I'm talking about LSST. Euclid is already taking data. We also have Roman in the future as well, hopefully. Okay, right, so that's the background stuff. So onto the interesting stuff. So there's 4 kinds of systematic effects I'll focus on, and I'll just basically, my aim here is to give a little bit of a flavor of the kinds of things that we're thinking about for these systematic effects for LSST. So I'll be frank up front. My primary area of expertise is going to be intrinsic alignment and some in PhotoZ, but I will speak about all 4. So If you have questions about the galaxy bias and the baryonic stuff, I may be able to adjust them, or I may direct you to the authors of that work. But anyway, so the four I'm going to talk about are baryonic effects, galaxy bias, intrinsic alignment, and photometric redshift related stuff. And I'm just going to give a flavor because there's not a lot of time, and then that can hopefully open up for the discussion as well, right? Okay, so I'll go through these one by one. So intrinsic alignment, as I said, my special interest, so I put that first. So just to explain basically what this means. So as I said, for lensing, we care about measuring correlations between often the shapes or the shear, which is the lensing induced change in the shape of galaxies. Now we know that galaxies can also have correlations in their shapes for other reasons, like that they actually physically have correlations in their shapes. So that's all this means. So intrinsic alignment is the intrinsic correlation in the shapes of galaxies. And so this can impact these 2-point functions in a few different ways. So this is an illustration of that. So we have an impact on the cosmic shear, so the shape case, in a few different ways. So you have a term associated with the fact that you could have two galaxies which are correlated in their shape due to being, literally physically near the same dark matter structure, and therefore having tidal effects correlating them. We also can have an effect on the galaxy-galaxy lensing case. Similarly, you could have galaxies in your source sample which are which have a correlation in their intrinsic shape to galaxies in your lens sample, just due to being physically tidally, or in terms of their environmental formation history, stuff like that, like physically associated with those lens galaxies. So these are the kinds of things we're worrying about for intrinsic alignment. We want to be able to model this and mitigate its impact on our cosmological inference. Okay, so here's just a flavor of the ways we're thinking about this within the LSST Dark Energy Science collaboration. So different projects that we have ongoing regarding this. So we've been working towards having mock catalogs which have realistic intrinsic alignment. So this is challenging because even in the case of big n-body simulations, because of storage requirements, requirements and stuff like that, it's not always the case that you actually have shape information for halos down to where, like subhalos where you would care about satellite galaxies. So even if you tried to populate on the basis of subhalo shapes, for example, realistic alignments, this isn't always possible. So one project which was led by Nick Van Alphen, who is a PhD student at Northeastern, was developing a HOD-like model that also incorporates sort of a realistic alignment signal with and without subhalo information. So this is illustrated with subhalo information, but there is a version of it that is without subhalo information that is able to well reproduce the intrinsic alignment signal in hydro sims. Other examples of work on this, we're looking at the possibility of using multiple shear estimation methods to extract the alignment signal. So the alignment signal is different in amplitude if you use different shear estimation methods, because of the sensitivity to different parts of the galaxy light profile. But you can take advantage of that to extract information about the scale dependence of the alignment signal. So there's a paper and an ongoing desk project led by Charlie Malin Geller, who's my PhD student, on this. We're also looking at the self-calibration method, which is basically a case where you try to split the source sample by photometric redshift to extract information. This is quite tricky. So Eske Pedersen is leading an ongoing project on this. And what we're finding is that it really may not work because of the photo Z uncertainties, as we'll get into in the next section. But it's an interesting method, and it has had some results that seem promising for stage 3. So we're still investigating that. There's also work looking into, okay, how do you map the so intrinsic alignment depends on a lot of things. So you care about your luminosity of your galaxies. You might care about other galaxy properties, like stellar mass fraction of sorry, that's not the right word, passive fraction of galaxies in certain parts of your sample. There's a lot of different parameters like you might care about, so color as well. And you can try to measure something from we have in LSST, we're going to have deep fields and for calibration of photo Z and other things. but also the main survey is wide, right? And so how do you take advantage of mapping from those deep fields if you can measure intrinsic alignments in those into the wider fields, which have a different distribution of those properties? So and do that in a way that doesn't induce biases, but keeps as much information as possible. So Jamie McCulloch, who's a postdoc at Princeton, is looking at a SOM, so self-organizing maps based method for that. So again, just a flavor, and I'm happy to talk more about any of those in the discussion. But in the interest of time, moving on to photometric redshift uncertainties, which are a huge concern. Obviously, some of you have spectra, love that for you, but we don't. So we care about the fact that, you know, when we're trying to estimate these redshift distributions, we have only these 5 bands, right? We have 5 photometric bands, and we have to get the redshifts of the galaxies from that and get the redshift distribution. And there are known outlier populations. There is obviously just dispersion between the true and the photometric redshift. This is a simulated case, but it gives you an idea of how you can't map these things one-to-one. Again, just to give a flavor of the kind of work that's going on. So in the top right-hand corner here, again, a self-organizing maps-based method that's in prep from Yanhao Zhang, who's a PhD student at Edinburgh, is looking at how you can, again, augment. So you need a spectra. You want to calibrate these things on spectra, right? We don't have our own spectra, but there are overlapping spectroscopic galaxy surveys that we can use for calibration. But this does fall down in certain parts of our parameter space. So can you augment those parts of that parameter space with simulated data and still meet our requirements? And it looks like you might be able to. This is sort of what this is showing. And so that looks like a promising method. Again, to do with the spectroscopic training set, we have this paper by TQ Zhang at University of Pittsburgh that's also in preparation, which is looking at the representativeness of the SPEC-C training set at higher redshift. So how does the figure of merit actually depend on how representative your high redshift training set is? And what TQ is seeing is, kind of interestingly, if I'm sorry about the small font here, but the line that kind of shoots up at the end here is the W not WA figure of merit. So as opposed to so I'm talking about the area of the contour in W not WA space, depends more sharply on the representativeness of the high redshift spectroscopic training sample than, for example, omega m sigma 8. Kind of makes sense because there's this redshift dependence, but interesting to see. And we have also this, the final figure on this slide is just work looking at, you know, different ways we can model the photo-Z uncertainty. So we have this sort of more traditional model of just a shift in the redshift bin means. You can also include a parameter for the widths or the variance in a Gaussian model of those bins. You can also try to model using methods like Gaussian process or PCA. And so this is using simulated data. Jaime Ruiz Zapatero looking at these different methods. And this is preliminary, but what's being found is that on simulations, it looks like these methods are all agreeing. And now we're on to baryons, because I'm not going to try to go back. So yeah, time-wise anyway, probably good if we carry on. So yeah, that's a little flavor of the kinds of things we're working on for photometric redshift uncertainty mitigation. The third of the 4 topics I'll briefly overview is baryonic uncertainties. So what I mean when I say baryonic uncertainties is the fact that that's basically at the beginning when we saw those like grayed out regions at the small scales, we had cut these small scales largely due to uncertainties in baryonic modeling. So this means effects from processes like AGN feedback, for example, is a big one. Gas physics processes that can impact the matter power spectrum at a level where we actually care about it in our weak lensing and clustering modeling, and which is going to affect our cosmological constraints. So this is just to illustrate this. So we have a bunch of different hydro simulations with different sort of modeling for the baryonic physics, the matter power spectrum on the left, propagated into an example, redshift crossbin of the cosmic shear on the right. And we see that, there's fairly significant deviations from the dark matter only power spectrum if you just ignore baryons. So what are we going to do about that? Because if we continue with the method of just cutting the smaller scales, as was done in DES, for example, we're going to increasingly have to cut more and more, because that's done based on the statistical uncertainty of the survey, which is getting higher. Now, I should say that's DES. There are other stage 3 surveys that take other approaches. I think KIDS actually does try and model this, for example. So I think this is, an example of where we're going to have to go, to actually try and model this properly. So within LSST desk, what's going on with this? So I will say, being totally honest, I think the baryonic modeling side of things is a little bit, we're ramping that up now. So as opposed to the ones I've said before, I think it's just kind of getting going. So it's maybe at an earlier stage. But we have been including, for example, different baryonic modeling tools in our theory library. So Core Cosmology Library, CCL, some of you may have come across it before. It's a public library that does a lot of validated theoretical predictions for cosmological observables. Everybody can use it if you want to use it. And now we have baryonic models. So we have the baryonification or BCM model included in there, as well as a model from Van Dalen 2019, and access to HM code, originally by Alex Mead, and I think one more as well, the Arico 21. So this is useful. We're still working on this, right? But you can use this in your modeling, and you can do some Fisher forecasts and see how it affects your constraints. This is all very, just showing we're working on the tools. There's also a group using the baryonification model to sort of baryonify existing n-body simulations. And one of the cases that's useful for is higher order statistics. So I'm showing the 3-point functions here for some different baryonification parameters. But this is by Avijit Bera at UT Dallas. I won't pretend to know too much about 3-point functions, but just to say this is also work in progress. There's also an effort that sort of should hopefully be launching soon, which is a challenge. So one of the ways we've liked to organize some of these efforts in Desk, and I think this comes out of a history in the lensing field, is to run so-called challenges, where we set up infrastructure that we think provides simulated data that is comparable to what we expect to the extent that we can. So in this case, it would be like data with realistic baryonic effects in a bunch of different cases, like on the previous slide. And we invite different folks who have developed different baryonic models. So for example, these here, maybe other ones, to kind of compete. And so this comes out of like sheer estimation challenges, I think, from the lensing community in the 2000s especially. And so we've run this for different things in Desk. We ran it for non-limber modeling. We run it for galaxy bias, which I'll come to on the next slide. But we're preparing one now for baryonic modeling to kind of get the lay of the land. And Tillman Troster at ETH is leading that. OK, final one, because I only have a couple of minutes left. Galaxy bias. So galaxy bias, of course, the case where just the name for the fact that galaxies are not unbiased tracers of the dark matter, right? The dark matter has certain correlation properties. Galaxies probably form in like the more massive halos, for example. So that's one, and it can be a stochastic mapping. We don't have a perfect picture of the dark matter from the galaxies. So what do we do about that? Okay, so very quickly again, borrowing heavily from the work of others in the collaboration. So like I said, there was a bias challenge. So looking at which models were the most appropriate given the simulated data that we had. And that was led by Andrina Nicola. And what was found there was that, so I guess I should say first, the sort of stage 3, early stage 3, we had a lot of linear galaxy bias models, so single galaxy bias parameter per redshift bin. Moving into some perturbative galaxy bias models in stage 3, But then we're looking at hybrid and sort of perturbation theory, effective field theory type models. And what was found was HEFT, so hybrid effective field theory, seems to perform well up to about K of 0.4 megaparsecs by H, which is great. But we also need to understand like what's the trade-off between including the full set of HEFT parameters versus can we get away with a few less and maintain some more precision. So there's work ongoing by that by Ottavia Tritero. I'm distracted by the timing signs. Okay, I think that's actually, oh no, one more thing, sorry. But wait, there's more. Yeah, so these things are not independent, unfortunately. That would be nice, but it's not the case. So we could treat all these like in our little isolated silos, but unfortunately that could come to bite us in the end. So there's all kinds of ways these can interact. So you can imagine that galaxy bias and baryons are not independent because the baryonic effects come from the galaxies to a large extent. So that there's kind of some exploration of that ongoing in like forecasting in a forecasting sense. You can imagine that galaxy bias interacts with the photometric redshift uncertainties because some of the methods for photometric redshifts are to do with cross-correlation in clustering with spectroscopic samples. So you have galaxy bias coming in there. Photo-Z and intrinsic alignment are kind of well known to interact via a degeneracy in the amplitude and redshift dependence. And there's, you can probably come up with a reason that all the rest of these should also interact as well. This is just an example of like one project that looked at this, which was trying to introduce a prototype for a joint model between the redshift distribution and the intrinsic alignment from the fact that they're in a magnitude limited survey, they should both depend on the luminosity function. So what if you introduce that as sort of an underlying parameter? And this was a desk project that came out last year. But there's a lot of work to do here as well, I would say. And I think with that, I should wrap up. And the summary is just that, hopefully I've shown you just a little flavor, a little taste of the kind of things we're thinking about, and given us something to start thinking about for the discussion in terms of astrophysical systematics mitigation for weak lensing and clustering with LSST. So thank you.
Questions, comments?
Well, I guess there's another systematic that comes with not considered, which is the number of galaxies which are not detected in the survey.
Yeah.
So suppose there are many lots of progressed galaxies on the line of sight. Could you marginalize over them or can quantify the effects of them?
Okay, so I think I'm going to repeat the questions, make sure I understood. So I think you're asking about the systematic that I didn't discuss, which was, I guess, what about the galaxies that we're not detecting? So do you mean it in the sense of like variable depth, or is there some other sense you're talking about?
No, simply we're not detecting them because we're not sensitive enough.
Right. So that would be to do with the magnitude limit being different.
Magnitude and surface brightness.
Yes. Okay. So I think so that's kind of what I meant by variable depth. So right. So I think we're talking about the case that. Right. Okay. I see what you mean. The surface brightness might be different. Yeah. So I haven't discussed that here, but yeah. So there are efforts ongoing to simulate what the effect is on the cosmological parameter inference of the fact that we know. Especially for LSST at intermediate year data releases, we're going to have a non-uniform survey footprint in this, basically. I think there might be something that I'm not fully getting in terms of the surface brightness, so maybe we can talk more about that later. But in terms of the non-uniform depth, that is a concern. And for example, we may have certain years of the survey where we opt to focus on for the weak lensing analysis because we do depend strongly on having a uniform depth. But I'd like to talk more about the surface brightness issue. Yeah.
I have two short questions and then some more which I'll save for later. So one was there was a slide where you presented a figure by Yunhao Zhang on the photometric redshift. I couldn't exactly follow what was going on there, so it would be nice if you just clarify that bit.
Yeah, sure. I can go back to that briefly. So,
Yeah.
right. So what is happening here, so we have a simulated, so yeah, I apologize for the small text, but we have a simulated data set for a complete spectroscopic calibration. This is in like a self-organizing map-based space. So basically, imagine that this 2D space has like a bunch of different properties mapped onto it. If you even just ignore the figure itself, but think that this represents like a higher dimensional distribution in terms of like maybe 4 or 5 different properties that you care about, and then you simulate the selection that we might expect in terms of like a realistic calibration set in that space. So you see you're taking out bits of what of the distribution that you care about. Then this is, what if you try to augment those areas where you're missing from that like higher dimensional parameter space you care about via simulations? Now this is our augmented set, and what do we end up getting? If we do that, we end up getting these redshift distributions, and here's our photometric versus true redshift plot. And the moral of the story is, this seems like it produces redshift distributions that are well specified enough to meet our cosmology requirements. But thank you. Yes, there's a lot of information in that slide.
Yeah, looks quite good. And the other question was about this remark that you made about the baryonic effects, where you said that we're only now catching up to, only now we've ramped up the efforts to understand them. But I couldn't follow like any of the strategies that you mentioned. I didn't understand how is it different from like the standard way of simulating smaller boxes, higher resolution galaxies, and just emulating baryonic feedbacks for painting baryons on dark matter only simulations.
Right. So I should say, when I said we are only now, I mean LSST desk is only recently focusing on this. Somebody online maybe would like to comment. But yeah, so you are correct that things like this is literally summarizing efforts in desk. But yes, like things like BCM and baryonification are very much within that, and that's been considered for quite a while. Things like emulating from HydroSim, so like including like BACO-EMU and stuff like that, very much. Yeah, I should have clarified more. This is building on that, but I feel like I'm just trying to say that in desk we are only ramping this effort up now. But thank you. Yeah.
Thank you.
Comments? Yeah.
Yeah, so can you hear me?
I can hear you okay, yeah.
Okay, so, stupid question is, when is LSST gonna first release? And then the second, maybe less stupid question, is so this unprecedented precision. So if I marginalize over many parameters, and then let's say omega baryon or SA, to what level of accuracy will LSST get?
Okay, so first question, first light, like first survey start, I believe, although this changes like all the time, I believe the plan for survey start is later this year or very early next year. That's survey start, right? The first data releases that we expect to be able to do lensing science on, I believe we are expecting mid-2027. So I believe that is the timeline, but don't hold the agencies to that. I'd have to double check. Second question, if you marginalize over all of this stuff, how does it look? I mean, this is the work in progress, right? So, I mean, I don't know that we have, so there's a whole team at the moment actually in desk called the Forecasting Topical Team, which is trying, so we had this document called the Science Requirements Document in 2018, which was like, what if we do what our best models for this are now? And that was sort of the benchmark at the moment. But we really, realized that like this is not what we didn't have any of this stuff around like hybrid effective field derivative bias and all these different things I'm talking about. So there's a team right now trying to redo that full forecasting analysis with our best systematics models now. I can probably find that like a plot that summarizes that, like their current status, but I don't have it in this slide deck, but it's a very reasonable question. I just don't have it to show you right now.
So let's thank Dani again.